In this video, let me explain the FSM that is related to your Lab 5. Good. So this is your lab handout, right? So if you look at your FSM section, which is basically in your CPU control plus your hard-coded program, the first thing you observe is that there is a reset signal. So always, any FSM you build needs to have a reset signal. So upon reset, it goes to state S0. Please don't confuse this S0 with this S0. So this S3 down to 0 is for your switches. This S0 is for your state 0. So if you think you'll get confused, you can call it state A. It doesn't matter. On your reset state, what you need to do is you need to tri-state all your buffers. So all these tri-states that you see, the inputs, which is your buff enable, should all be Z's or high impedance, and reset all your registers to zeros. So your R1, R2, and R out all need to be reset into 0. Good. Then when reset is deactivated, the machine transitions to a next state, which basically Si plus 1 at every positive edge of the clock. So the keyword here is on pause edge of clock. On every pause edge of clock, you go from S0 to S1 to S1 to S2, S2 to S3, and so on and so forth. Good. In state 1, which is here S1, the thing that you need to do is the machine reads the data on the external switch and load it into register R1. So before you run your state machine, you should have set the value on your switches so that the state machine will come to state 1, upon which it will read your slide switch. So let's say 1010. I'm making something up, right? So you want to load that value into register R1. So the value 1010 needs to go into R1. So the way you do that is you first, quite logical, right? You need to enable this tri-state. So when you enable this tri-state, 1010 will go on the bus, followed by enabling this buffer so that the 1010 will be available at the data input of R1. So then you need to enable R1 so that on the next clock cycle, the value of 1010 will be read into R1. So it's a three control process, right? So you need to enable this tri-state, enable this tri-state, and then enable this R1 so that on the next clock cycle, whatever data which is written on your slide switch will go into R1. So that's how you will basically, that's the things that you need to implement when you're in state 1. How would you do this? Well, open the respective buffers to put the data on the bus, right? And then enable R1 so that on the next pause edge of clock, R1 loads the data corresponding to the switches. But remember, R2 should be disabled. Otherwise, the data will also get loaded into R2. Yeah, this is a very important point, guys. This R2 enable should be disabled, right? Basically, this R2 enable and this tri-state, right? Disable these two so that your data only goes from the switches to the bus to R1. It does not overwrite your R2. Very important. Next, in state S2, load an integer R3 or load a integer value 3 into R2. This is akin to load immediate instruction or LDI instruction. Okay, so if you have taken a computer organization class before, right, you probably have know some idea of what a load immediate instruction is. So load immediate basically means that in this case, right, all the inputs to your registers R1 and R2 comes from your bus. Okay, but the problem is you can't do a load immediate value. Load immediate value basically means you get the flexibility. So it need not be that you want to load the value of 3. You can load any value onto R2. That's what a load immediate instruction is. So in here, in R2, right? So along with this signal, which is basically a tri-state buffer, which goes to your R2, you also need to somehow mux the value of 3 into the data input of R2, right? I'm basically giving out how you should implement this design. So it's not exactly like this. Along at the output of this tri-state, you put a 2 to 1 mux. Not a 2 to 1 mux, but it takes 2 inputs and 1 output. And the other input to the mux is nothing but your value 1010. And the mux select line that you have, right, that should basically be selected in S2. So basically in S2, the FSM will tell that, hey, it will tell the mux to pass the value of 0011 into R2 and not the tri-state buffer. So again, if you have questions, log into our office hours and we'll help you out with this. And then basically, it's every instruction every state he tells you what needs to be done. So it basically just look at what needs to be done. So for example, if you want, let's take S5. What does S5 say? R out is basically R1 or R2. So when you are in S5, you basically need to provide your ALU control signals such that it performs the OR operation. And then you need to enable your ROUT enable so that that value of that output from your ALU gets loaded into ROUT on the next clock cycle, and so on and so forth. So it's basically, it's very simple, it's very straightforward, one after the other. So you would have observed that there are 9 states. So this is a 9-state machine. Good. So this line again is very important, guys. When you get to S9, you display the result on your 7-segment display and stay in this state until the reset is pressed, in which case you restart the process from S0, right? So when you get to S9, you stay in this state. You don't go back to S0. What will happen if you go from S9 to S0 is basically whatever you've done so far, it will keep doing this forever, right? Your state machine is basically hard coding your program, and your program needs to terminate somewhere, and it terminates when it comes to S9. When it's at S9, you stay at S9 so that when you hit reset, the FSM will start at your state 0, and then it will basically do this all over again. So this is basically how your FSM should work. And if you read your FSMs carefully, you will observe that this is basically a series of instructions that it is performing. And series of instructions is nothing but a program. So thus your FSM implements your program. This is basically a hard-coded program. Quite simple, quite straightforward. If you've seen all the videos on FSMs up to this point, you should be able to implement this probably in an hour or two, and you can then write the model simulations. All right, good luck, guys.